Hello everybody, Root Beer here. We're going to continue our look at the 2014 CSMC, that's the Canadian Senior Paper. We're almost done Part A, so this will be the last final answer, no written solution necessary question. So let's take a look at question 6 in Part A. Alright, question 6, 10 lockers are in a row. The 10 lockers are numbered in order with the positive integers 1 to 10. Okay. Each locker is to be painted either blue, red, or green, subject to the following rules. 2 lockers, numbered M and N, are painted different colors whenever M minus N is odd. And it is not required that all 3 colors be used. So these are our 2 conditions. In how many ways can the collection of lockers be painted? Okay. So this is going to be a straightforward counting question. So we're going to have to do a little combinatorics, probably have some choose notation or something in there. Now, it is not required that 3 colors be used isn't all that restricting. Okay. But 2 lockers numbered M and N are painted different colors whenever M and M minus N is odd. That does sound like a very restricting rule. So how about we explore that? When does that happen? Okay. So M minus N is odd means different colors. Well, we don't really know what M and N are. Obviously, they're numbers between 1 and 10. But if we're talking about a difference being odd, we could have a couple cases. We could have M and N, and then M minus N. So if M is even and N is even, well, the rule doesn't say anything about these 2 lockers. They could be the same color or not. How about if M is even and N is odd? Then we'll have odd. So if M is even and N is odd, the difference is going to be odd. So that's important. If M is odd and N is even, that difference is also odd. And if they're both odd, it's even. So the difference between 2 odd numbers like 17 and 7, that's even. So our first rule tells us that an odd locker and an even locker must have different colors. But that's it. As long as it's an odd locker and an even locker, they have to have different colors, nothing else. Even and even lockers, they could be the same, they could be different. Odd and odd, they could be the same, they could be different. So, we get 2 groups here. 2 groups of equal sizes. The odd lockers and the even lockers. Now, within the even lockers, no relationships. Nothing that we can do. So they could all be blue. Some of them could be red. Some of them could be green. But as soon as one odd locker is green, none of the evens can be green. So if we know an odd locker is blue, no even locker can be blue. Otherwise, they'd have an odd difference, and that would break that rule. And of course, the same goes for red and green. All right, once we have one color for one group, that the other group cannot have that color. So this leaves us with a couple options. So either we say, pick that the odds are all going to be red and then the evens are a mixture of blue and green, or maybe the evens are all green and the odds are blue. So here's where the second rule comes into effect. We don't have to use all the colors. So we have two cases. Either they each get their own color, and the odds and the evens, they're each monochromatic, obviously with different colors. Or all three colors are used. And that means that one group gets one color, the other group gets two, and has to use both. Right? We can't say the evens get blue and the odds get red and green, and then have the odds be painted all red. Then they're not using both red and green, and that's actually this first case where both groups use one color each. So these are our two cases. Now we just need to figure out how many ways we can do that. Actually, let's number our cases. So we'll call this 1 and this 2. So for case 1, so we have three colors. We need to pick a color to paint all the evens. So we have three choices: red, blue, or green. Two colors left over for the odds, so maybe the evens are blue, the odds get red, and red or green, not both, because we're only using two colors here. So that's two choices. And once we have chosen our colors, we know exactly how the lockers are going to be worked. They're all going to be painted the same color. There's going to be 6 different ways. So if we were to pair evens and odds, we could have blue-red, blue-green, red-green, red-blue. or green, red, green, blue. That's 6 different ways we can pick these. Okay, so that's 6. Now for case number 2, I assume this is going to be a little more complicated. First, we need to know who's going to be monochromatic. So we have 2 choices, even or odd, for the group that gets just one color. And we have 3 choices for that one color. Okay. Now each group, odds and evens, they both have 5 lockers, either 1, 3, 5, 7, 9, or 2, 4, 6, 8, 10. So we're going to say, actually no, let's call them color 1 and 2. Color 1 and color 2. So we have 5 lockers. We could have all 5 lockers be color 1, and none of the lockers be color 2. We could have 4 of them be color 1, and 1 of them be color 2. 3, 2, 2, 3, 1, 4, and then none of them could be color 1, and 5 of them could be color 2. Now these 4 in the middle are all valid, but these 2 are not. And you'll notice the symmetry in that table means that we don't need to designate who's going to be color 1 and who's color 2, so we don't need to make a choice there. If we were going to say the first color is the one that's used the most, we'd use half our table, but we'd have to have a choice of which color is color 1. Okay? So that might be a little place where you might get into a bit of trouble if you were trying to think this one through. So once we've picked how many lockers get each color, well, we have to actually pick the lockers. We have 5 lockers, and say we're choosing 3 of them to be painted with color 1. 5 choose 3 different ways. So K goes between 1 and 4. So this means that we have 2 ways to choose which group gets the 1 color, 3 ways to choose that 1 color, and then finally 5 choose 1 different ways to paint with color 1. 5 choose 2 to paint with color 1. 5 choose 3 to paint with color 1, and 5 choose 4 ways to paint with color 1 out of the remaining 2 colors. So that's 6 times 5 plus 10 plus 10 plus 5. If you need to, you can go back to the definition of choose notation if you want to, as 5 factorial over k factorial times 5 minus k factorial. Or you can just remember the rows of Pascal's triangles, because Pascal's triangle, because we're only on the 5th row here. So that's 6 times 30, so that's going to be 180. And let's not forget our 6 original, if we just use 2 colors. So there's 6 plus 180, which is equal to 186 ways to paint the lockers. Alright, so we get a total answer of 186, and we could just put that in the little box provided in the answer booklet. And that does it for question number 6. So now we're done. We're done part A on the 2014 paper. So in the next video, we're going to be taking a look at part B, and that's the actual written solutions. So yeah, leave a like on the comment, or leave a like on the video. Leave a comment if you want to. Maybe you got the answer in a different way, and I would love to see that. And if you like these videos and you want to keep being up to date on them, feel free to subscribe. But either way, I'll see you guys next time for part B of the 2014 CSMC paper.